This is another episode of DIY with Arduino, or Do It Yourself with Arduino, which highlights my work in progress and experience with this development board. The topic of this video is about controlling the servo, and we will be using the Arduino Mega 2560 R3. So let's start with how the setup is made. But before that, I would like to show the servo, the kind of servo we are using right now, just to have a good look of it. So that is a Tower Pro micro servo, about 9 grams in weight. Now let's proceed to the wiring connections. Servo has 3 wires. If you are following my pointer pen, this is an orange colored wire. That is the data wire going to the servo. On the middle is the red wire. That is a power wire supplying the servo. And on top, that is a brown colored wire, and that is the ground wire of the servo. So those 3 wires are now connected on the corresponding pin on the Arduino board. So the ground wire is connected via this black wire connector on the ground pin of the board. So that pin over there, and the red wire is supplying 5-volt supply to the servo, and that is connected to a 5-volt pin on the board. The data wire, this wire is now connected to the digital pin number 9 of the Arduino board. An important advice: in lieu of this setup, it is best to power the servo from a separate power supply, such as battery. All you need is to connect the ground and supply wire of the servo to a battery terminal, leaving only the data wire connected to a digital pin you select from the board to avoid overcurrent on any Arduino pin. Anyway, with this setup, it's working well for many hours, but again, it is best to have a separate power for your servo. This setup is made for the sake of experimentation and trial and error to expand the knowledge and experience. So in addition to this setup, we are going to connect also the data wire of the servo to a PC-based oscilloscope. And we are now going to connect the oscilloscope probes on that wire. So now the probe shown is connected to data lines or data wire that links pin 9 of the Arduino and the data wire going to the servo. So we will be able to view the electrical pulse passing to that data line, and this will greatly expand our ideas how the servo works. So shortly we can view that signal trace on the desktop screen. So on the screen, we have the view of the Arduino sketch on the left. So the same sketch now loaded to the microcontroller. And at the center is the oscilloscope view or window, which is now showing the signal trace sent by the pin number 9 of the Arduino through the data wire going to the servo. So on the right, we have the live feed from the webcam showing the Arduino and the movement of the servo. The signal trace on the oscilloscope window is basically generated by the microcontroller following the uploaded sketch that is shown on the left. So let's take a moment to observe how the servo arms moves following the signal trace. and that is a pulse width modulated signal that is being read by the oscilloscope through its probes on the data wire of this servo. So we can clearly see that the servo arms moves or sweeps from one end to another, and it points itself upward as the pulse narrow its width, and points downward as the pulse widens its width. Next, let's see what is the width of the pulse at each end points of the servo arm. And to see that, we need the oscilloscope to read the how wide is the pulse, and we need to change the scale of the view to 10 milliseconds per division. And there you can see, if we are following the cursor arrow, you can see now the data at the bottom of the screen. So it's quite fast to read the data. So what we will do, we will do some minor editing on this sketch by putting some delay. Let's delay the sweep of the servo arm once it's reached its maximum and turning point. Let's delay that turning point to around 5 seconds. Yes. So now we will be able to see the maximum and minimum reach of the servo arms. Let's now upload that. So there you go. We are at 2.4 milliseconds when the servo arm is pointing downward, and 560 microseconds as the servo arm is pointing up. So in short, we can see that again the servo points up at about 500 microseconds and points down at a pulse of about 2400 microseconds wide. So that is within a 20 millisecond cycle period. So this one here I'm pointing at, that is the width of the cycle period. A cycle period is a total of the positive pulse and the low pulse. So if we try to make a closer look, so that is the positive pulse, the one with the rising edge, and the low pulse is the one at the zero, at the align the x-axis. Let's try another zoom. Yes, the total channel, the total cycle period is this one plus this one. So that is around 20 milliseconds. So that is the range of pulse which makes the servo travels. So going back to the sketch, this sketch is included on the example folder library when you install the Arduino, and let's look at that. This one here, the sweep file name, and it uses the built-in servo library primarily used for controlling the servo. So that's quite complex for the beginner to grab immediately. So what we will do, we will rewrite it later, where we can easily understand how the servo library works from its basic form, or from the most simple sketch we could show. So but before we go from here, to summarize, what this sketch does is it tells the microcontroller to create a pulse at a range of approximately, I should say, 500 to 2400 microseconds wide. That is a positive pulse, and which turn the servo on its maximum endpoints. So again, servo moves around a half circle that is between 0 to 180 degrees approximately. So let's try to get to a more basic sketch and edit the sketch to, or so we can see and we can explain further the in more simple way. So let's try to remove the unnecessary. We'll show only those that are really necessary, or as a minimum to control a servo. So these are the minimum statement to control the servo. First, we have to include the this statement. If try to follow the cursor, the include statement, and then create a servo object and name it, in this case, my servo, or any name. And then within the void setup, you can attach the servo to a digital pin using the attach command before the name of servo you declared before, this the one I'm shaded at. So, and indicate your what pin number is the servo data wire connected to. And after that, within the loop functions, you can write the position of the servo using this this simple statement, the write statement, and of course always write before the command the name of servo you declared as an object. So the position, you can write any desired position within the range of 0 to 180 degrees. So what we will do, let's see. Let's start with the 0 degrees, and let's take note what is the reading of the oscilloscope. Now, as you can see, the servo arm moves upward, and we're getting a 560 microseconds of pulse, or I should say in other terms, 560 microseconds wide of pulse. The width is, that is a time in terms of time reference. So again, to go forward, let's try the maximum, the other end, the other extreme end, and that is 180 degrees. And now we can see that it's around 2.4 milliseconds wide. So just to add more to the example, let's try 90 degrees. So that's around 148 milliseconds. And next, 45 degrees. That's around 1 milliseconds. And 135 degrees. That's around 2 milliseconds. So you can play around by just changing the value between 0 to 180 degrees, and you can get the desired position of the servo arms. Now to conclude this example, we have learned that a servo can be controlled by creating a pulse or sending a pulse between approximately 500 to 2400 microseconds within a 20 milliseconds cycle period, or that is an equivalent to 50 Hertz. Now, knowing this range, we can also control the servo by creating the same range of pulse without the use of Servo Library. And in the next example, we can do that by creating a digital output signal. That is the same way as you first try to toggle an LED at a specified time interval. So let's do that, and let's start with a very simple sketch that is available also in the example folder of the Arduino. The sketch named blink, meaning this blinks an LED. Yes. So what this sketch does is it blinks an LED when the digital write command set the desired pin. Let's say in this case, let's edit it, pin 9. And if you have an LED attached to pin 9 and one wire to the ground, or its ground wire attached to the ground, the LED will turn on. Now this example provides a delay of 1 seconds. That means the LED will turn high for 1 second, and it will turn low or switch off for another 1 second. So it's blinking in that time interval. So what we will do, we will change the interval so that we will match the range that the servo will be able to interpret to move its arm from one end to another. So what we will do, we know that the range for the positive pulse, in this case we will consider the high pulse, a delay should be around 500 microseconds to 2400 microseconds, as we have learned during the example on the using the servo library. So we will start by 520 microseconds. That will position the servo arm upward. So it's not a delay, it's a delay microseconds. Yes. And for the low pulse or the zero pulse, those lines that is along the x-axis, that should be maintained to a maximum of 20 milliseconds. So for an allowance, let's make it consistent with the 19 milliseconds. So that 19 plus 0.520, that's around 19.5, still close to 20 milliseconds. And when we do it with 2400 microseconds, that's around 2.4 plus 19 milliseconds, that's around 21.4 milliseconds. So it's still close to 20 milliseconds, and that should work fine. So let's start first 520 microseconds, and yeah, let's edit this one, 9. So all are now set to pin number 9. Let's remove the unnecessary. Okay, let's upload that, and it should turn yes, it turns the arm to the top position, and we are reading around 520 to 540 microseconds of positive pulse. and as usual the low pulse or the zero pulse is 19 milliseconds. So we can change that a little bit. Let's say 515. You can play around if you try to adjust the, or let's say 540. If you wish to adjust the verticality of the servo, if you are that picky. Now let's try the 2400 microseconds, and it should turn or point down the servo arm downward. So that's it, and you can try to play a little bit with the value, let's say 350, to align the servo vertically. Yeah, so now the arm is close to vertical position, and we are getting around 2.40 to 2.38 milliseconds. So if we recall, if we want to turn the arm to 90 degrees, we should have around 1500 microseconds, and let's do that. Yes, and with a little adjustment, let's say 450, 1450. Yes, more or less that's perfectly horizontal. And if we recall again, we need a 1000 microseconds to position it 45 degrees, and 2000 microseconds to position that in 135 degrees. You can play with the values within that range, but don't go below 500 microseconds or above 2400 microseconds, as it may push the servo arms beyond its limit against the stopper, and it could damage your servo. So as a best bet, you try for a different from a different manufacturer or brand of servo. You can try the middle. The first starts with the 2000 microseconds if you want to reach the maximum value, and play that up to 2400 microseconds until you align the servo. Or if you want to try to align the servo at the 0 degrees position on the other end, you can start like not 500, you can start with 600 microseconds and move from that value much lower until you align again the servo to a vertical or horizontal position, because the servo, inside the servo there is a stopper, and if the servo arm is trying to push its way to that stopper, it could damage the servo and overheat the coil inside the servo. So that's the uh, simple way of doing, or doing it in another way other than using the servo library. And I have already prepared another sketch using the same method. I made another sketch that would sweep the servo arms back and forth the same way as the sweep example using the servo library, except that we will use the same method we have just shown using the delay functions or the delay timer. By the way, the servo library uses a timer 2 function, whereas this method uses the timer 1 function because of the function delay microseconds and delay. This uses a timer 1 function. There are, in Arduino Mega, there are, I believe, around 5 timer functions, from timer 0, timer 1, timer 2, timer 3, timer 4. I'm not sure if there is a timer 5. But anyhow, let's proceed with this example. And the very basic explanation or about the sketch is simply to sweep a pulse signal that range from 520 microseconds. It will go forward, making the pulse wider up to 2350 microseconds, and then it will sweep backward again from 2350 microseconds. It will go as narrow as a 520 microseconds wide. That is at the interval of 10 microseconds. So if you will calculate further the 10 microseconds, that is equivalent of 1 degree. If you will try to ratio and proportion it using the Servo library from range of 0 to 180 degrees, the 10 microseconds, that's more or less equivalent to a 1 degree turn. So for demonstration, let's upload it. I will not discuss this further. You can, you can examine it as a homework. Yes. Let's have a closer look. If you notice the way the oscilloscope is tracing the data, uh, it appears that every time you exit the for loop, this one, the one I have shaded, it switch off the pulse to low, and then if once it start again on the next for loop by sweeping it back again, and it start to switch on again. Unlike the one we have seen on the servo, using the servo library, it does not turn off the pulse, but it's in the same it works the same way. Or maybe the it's just the reading of the oscilloscope. If we will say try to make it faster, maybe you would almost not notice that. I see. So that's it for this example. The knowledge of controlling the servo will be useful when we go further with the BLDC motor, or brushless DC motor, commonly used on RC model airplane and cars and whatever, etc. So, thanks for watching.